Okay, picture this. You're in Florence, Renaissance Florence, and there's this artist, Filippo Brunelleschi.
Right.
And he's got this setup, an easel, a mirror, some wires,
Hmm.
right there by the half-built cathedral. People must have been thinking, what is he doing?
Yeah, absolutely. He was showing off his new discovery, basically, the laws of perspective.
Exactly. A way to make a flat painting look totally 3D. And, well, it changed Western art for, what, like 450 years?
Easily. But here's the twist, the really wild part.
Okay.
That artistic technique, figuring out depth on a canvas, it actually kind of accidentally laid the foundation for modern crypto.
For Bitcoin security and, like, secure websites?
Elliptic curve cryptography. It's a direct, though very long line from Brunelleschi's painting demo.
Wow. Okay, so that's our mission for this deep dive then. Trace this incredible path, 6 centuries, 2 continents.
Involving ideas like infinity, mathematicians in pretty dramatic situations.
Right. And for our listeners, especially, if you're preparing for the UPSC exams, this is just a perfect example.
Absolutely. How completely different fields can connect over time.
Yeah, understanding those fundamentals and seeing where they pop up unexpectedly, super relevant for mains, maybe even prelims spotting those connections.
You really need to track the logical steps, how one idea built on the next.
Okay, let's dig in. Brunelleschi's demo. What exactly was going on there? Around 1415, 1420?
Yeah. Somewhere in there, he painted the baptistry, the building right near the cathedral, using this setup. It seems this was the big reveal of his perspective laws.
And the key thing wasn't just making realistic art.
No, not just that. It was establishing what you could call a visual geometry, a mathematical system almost, for artists to create that illusion of space.
A visual geometry, okay. And that ruled art for ages. But how do we get from there to, well, hardcore mathematics?
That's the bridge, merging that visual geometry with formal Euclidean geometry.
Yeah.
Lines, points, planes, stuff we learn in school.
Right.
And that brings us to Gérard Desargues, 17th century French mathematician.
Desargues doesn't ring a bell immediately. Was he famous back then?
Not really, no. His work was super obscure.
Oh, why?
Well, for one, he used really difficult technical language. And his main book, tiny print run, like maybe 50 copies.
50, that's it.
Yeah, and apparently the publisher even bought back some and destroyed them. So almost nobody saw it.
Wow, so how did his ideas even survive?
Mostly thanks to Blaise Pascal, the famous mathematician and philosopher. He was a big fan, understood Desargues' work, and even added his own theorem to it.
Okay, Pascal helped keep it alive.
Yeah.
So what was Desargues' big contribution, the one that got overlooked?
His killer idea was adding points and lines at infinity to good old Euclidean geometry.
Points at infinity. Okay, that sounds pretty abstract.
It is a bit mind-bending at first.
Yeah.
But think of it like extending the playing field of geometry.
How so?
Well, normally, parallel lines never meet, right? That's the definition.
Right.
In Desargues' system, you add a special point at infinity where all parallel lines do meet. Suddenly, every pair of lines intersects at exactly one point. No exceptions.
Huh. So it simplifies things in a weird way.
Exactly. It unifies concepts. Same thing with shapes like parabolas and hyperbolas. Desargues showed they're basically just ellipses, but with 1 or 2 points touching that line at infinity, it brings everything together neatly.
That really is a different perspective, pun intended. Okay, so Desargues plants the seed, even if it doesn't grow much right away. What happens next?
Well, yeah, his ideas kind of languished for over a century. The next real push came from another French mathematician, Gaspard Monge.
Did he find Desargues' book?
Doesn't seem like it. He apparently worked on similar problems independently and came up with similar results. Happens sometimes in science and math.
Independent discovery. Okay. But wasn't there someone else who really pushed these ideas forward? Someone with a dramatic backstory?
Ah, yes. You must mean Jean-Victor Poncelet, early 19th century. Another French mathematician, but also an engineer.
Right. A cool Polytechnique grad, military engineer, ended up in Napoleon's invasion of Russia.
That's the one.
Yeah.
And things went very badly for the French army there, as you know.
Catastrophically. What happened to Poncelet?
During the awful retreat, the Battle of Krasnoye, he got separated, probably presumed dead. He was captured by the Russians.
Oh, wow.
And then forced on this brutal march. Over 700 miles just to get to the prisoner camp in Saratov. Saratov was like 2,000 miles from home.
Unbelievable. How do you even survive that, let alone think about math?
It's incredible. But apparently, to keep his mind occupied, while he was a prisoner, deprived of books and comforts, he tried to reconstruct all the mathematics he knew.
Just from memory?
Yeah. And in doing so, he ended up expanding on Monge's work and basically recreating Desargues' projective geometry from scratch.
Whoa.
And, maybe being stuck in that vast, seemingly endless Russian landscape, that idea of points at infinity really resonated with him.
That's a powerful thought. Facing infinity, literally and mathematically.
Could be. Anyway, when he finally got back to France after the war, he wrote it all down. His big 2-volume work on projective geometry came out in 1822.
And this time, people paid attention.
Much more so, yeah. He got a much better reception than Desargues' work ever did. Maybe the story helped, maybe the timing was just better.
Okay, so projective geometry is finally established now.
Well,
Elliptic integrals, elliptic curves. That feels like a different direction entirely. How do they connect?
it does seem like a jump, but there's a link. Around the same time Poncelet was publishing, you have this brilliant Norwegian mathematician, Niels Henrik Abel.
Abel, right.
He was working on something called elliptic integrals. They're related to calculating the arc length of an ellipse, notoriously difficult calculations.
Okay.
Abel's genius move was to look at the inverse of these integral functions. And he found that these inverse functions, which he called elliptic curves, were much, much easier to handle mathematically.
So flip the hard problem around and it becomes simpler.
Pretty much. It was a major insight. Sadly, Abel died incredibly young, only 26.
Tragic. Like so many brilliant mathematicians of that era.
Yeah. But his work on elliptic curves opened up a whole new field. And then just a few years later, in the early 1830s, you get Évariste Galois.
Another French prodigy, another tragic end. Died in a duel at 20.
That's him. But before that, he laid down the foundations of group theory.
Group theory. Okay, refresh my memory. What's the core idea there?
Well, very simply, group theory studies sets of objects and operations you can do on them, where those operations follow certain rules. Like you combine two things in the set, you get another thing back in the set. It's fundamental to abstract algebra.
Got it. So we have projective geometry, elliptic curves, group theory. Still feels like separate pieces.
We need one more piece to really tie elliptic curves together. We need to connect projective geometry back to the standard Cartesian coordinate system.
Oh.
XY graphs.
Okay, who did that?
That was August Mobius, a German mathematician. Yes, the Mobius strip guy. He developed something called homogeneous coordinates.
Homogeneous coordinates.
Yeah, think of it as adding an extra coordinate. It's a clever way to represent those points at infinity from projective geometry using numbers. And this turns out to be absolutely essential for elliptic curve cryptography.
Okay, so Mobius links the coordinate plane to projective geometry, including infinity. Now what?
Now we jump to 1901, Henri Poincaré, another giant of French mathematics.
Okay.
He has the crucial realization. The points on an elliptic curve whose coordinates are rational numbers fractions, basically they actually form a group in the sense of Galois group theory.
The points themselves form a group. How do you add points on a curve?
Right. It's not like adding numbers 2 plus 2.
Yeah.
It's a specific geometric operation. You take 2 points on the curve, draw a line through them, where that line hits the curve again, gives you a related point, and then you reflect that point across the x-axis usually. That's your sum.
Mm-hmm.
And the amazing thing Poincaré showed is if you add 2 rational points this way, you always get another rational point back on the same curve.
And that only works if you include...
Exactly. It only works consistently if you use Mobius's homogeneous coordinates, which gracefully handle that point at infinity. That point acts like the zero element in the group addition.
Okay. And there was another property, abelian.
Yes. Critically, these elliptic curve groups are abelian, or commutative, meaning it doesn't matter in which order you add the points. Point A plus point B is the same as point B plus point A.
Right, like regular addition. Okay, so deep breath. We have elliptic curves defined with coordinates, points forming a group, addition defined. How on earth does this become internet security? That still feels like a huge leap.
It was a huge leap. And it didn't happen until the mid-1980s. That's when 2 researchers, Victor Miller at IBM and Neil Koblitz at the University of Washington, independently had the same brilliant idea.
Which was?
They realized that the properties of these elliptic curve groups were perfect for public key cryptography.
The whole public-private key thing that secures so much online.
Exactly. Quick refresher. You have a private key you keep totally secret and a public key you can share. You need both to unscramble messages.
Right. So how do elliptic curves fit in?
Okay, simplifying a bit. Everyone agrees on a specific elliptic curve. And a starting point on that curve, let's call it G. You pick a secret random number, your private key, let's say A. You add G to itself A times, using that special curve addition. The resulting point on the curve is your public key. Let's call it A.
Okay, so my public key A equals AG.
Basically, yeah. Scalar multiplication using the group operation. Now, someone else does the same with their secret number B to get their public key D, A to BG.
Got it.
You share your public keys A and B. Now you take their public key B and multiply it by your secret number A, so you calculate a B.
And they take my public key and multiply it by their secret B, so they get BA.
Exactly. And because the group operation is commutative, abelian, AB equals ABG, which is the same as BAG, which equals BA.
Whoa, so we both arrive at the exact same point on the curve.
Precisely. Without ever sharing your secret numbers. That final point is your shared secret, which you can then use for standard encryption.
And the security comes from?
The security comes from how incredibly hard it is, computationally, to figure out the secret number A, just by knowing the starting point G and the final public key point A. It's called the elliptic curve discrete logarithm problem. Easy to multiply, very hard to divide, basically.
Okay, that's clever. Really clever. And this elliptic curve cryptography, ECC, it's actually quite new in the grand scheme of things.
Yeah, relatively speaking. The first real toolkits for developers only started appearing around 2004.
So it missed the first wave of internet standards.
Right. But then Bitcoin launched in 2009, and its creators chose ECC for securing transactions.
Ah, so crypto, the currency kind, really pushed ECC into the mainstream.
It definitely raised its profile and led to more implementations, yeah. Although it's worth noting that RSA is still probably more widely used overall across the internet.
But I hear ECC has some big advantages over RSA.
Oh, definitely. The main one is efficiency and strength. ECC gives you much stronger security for the same key size compared to RSA.
How much stronger?
Well, like, a 256-bit ECC key is generally considered about as secure as a 3072-bit RSA key.
Wow, that's a huge difference. Most RSA keys are 2048 bits, right?
Commonly, yes. So, 256-bit ECC is significantly stronger than that standard RSA. And these shorter keys mean calculations are faster.
Which means?
Faster secure connections, like when your browser sets up HTTPS. Faster digital signatures. Less processing power needed on servers, which saves energy. It's just more efficient.
And is it relevant for the future, like with quantum computers?
That's a really active area of research. While standard ECC could potentially be broken by large quantum computers, the underlying mathematical structures are being used to develop new kinds of post-quantum cryptography that would be resistant.
It's just staggering to think this all started with Brunelleschi trying to draw buildings realistically.
I know. From Renaissance perspective, techniques through obscure 17th century geometry, prisoners of war doing math, abstract group theory, all leading to the algorithms protecting our emails and bank accounts today.
It's an unbelievable thread through history.
It really is.
Yeah.
It just perfectly highlights how curiosity in one area, even something like art, can spark developments in completely unexpected fields centuries later. The connections are often hidden deep.
It really makes you stop and think, doesn't it? What other ideas, maybe from history or seemingly abstract science, are just sitting there waiting for a future application we can't even imagine yet?
Exactly. That interconnectedness of knowledge is so powerful.
And again, for anyone listening who's deep in UPSC preparation, this is such a prime example, wouldn't you say?
Absolutely. It shows the practical power of fundamental concepts, the importance of intellectual history. Look for these kinds of links in your studies connecting science, history, philosophy. It adds so much depth. Great for mains, great for prelims too.
Couldn't agree more. Just fascinating. Well, if you found this journey from Renaissance art to modern encryption as mind-bending as we did, please do give us a like and subscribe to the channel for more deep dives like this one. Let us know in the comments if you have questions or other tangled histories you'd like us to unravel.
Yeah, we'd love to hear from you.
And just to note, our exploration today drew heavily on reporting and information from Scientific American. Thanks for tuning in.